Today we discuss section 5.2 residue classes and complete residue system. Consider a fixed modulus m greater than 0. By theorem 5.1 we know that A related to B if and only if A congruent to B mod m is an equivalence relation. For A belongs to Z, the equivalence classes of A is called the residue class of A modulo M. It is denoted by A cap. That is, A cap is equal to set of all x belongs to Z such that x related to A. This is equal to x belongs to Z such that x congruent to A mod M. Therefore, being the equivalent classes, all the residue classes possess the following properties. That is theorem 5.10. For a given modulus M, we have A cap is equal to B cap. Residue class of A is equal to residue class of B if and only if A congruent to B mod M. Second, we have two integers x and y are in the same residue class if and only if x congruent to y mod M. The third one is the M residue classes, say 1 cap, 2 cap, and all the way up to M cap, are disjoint and their union is the set of all integers. We prove A cap equal to B cap if and only if A cap and B cap are the same equivalence class. If and only if A related to B, because this is the property of the equivalence relation. If two elements A and B are equivalent, if and only if their equivalent classes are the same. If and only if A congruent to B mod M. To prove B, we assume that x comma y belongs to an equivalent class of A. This shows that x is congruent to A mod M and y is congruent to A mod M. But we know that this congruence is an equivalence relation. So you can get x is congruent to A mod M. On the other hand, you can write this as A is congruent to Y mod M due to the symmetry implies using the transitivity on these two congruences relations, we have x congruent to Y mod M. This implies for the converse, we assume that x is congruent to Y mod M. So using the property of equivalence relation, we have x cap is same as y cap, say A cap. So we can say that x belongs to x cap and y belongs to y cap, and hence x and y are in the same equivalent class. Hence x and y are in the same residue class. Now we can prove C part. First we will prove that these equivalent classes are disjoint. So that is very easy, because if you assume x belongs to intersection of any two of these equivalent classes, say I cap intersection j cap, we have x is congruent to and and x is congruent to j mod m as well. From these two congruences, you can get from the first we can write I congruent to x mod m and x is congruent to j mod m. This is because of the symmetry. Then using the transitivity, you can get I is congruent to j mod m. This implies I cap equal to j cap. Yeah. From these two mode relations, you can get I and x is congruent to j, because if we assume I cap intersection j cap, from these equivalent classes or residue classes, these I comma j lies in between m and 0, and now we have I congruent to j mod m. So using this and these congruences, you can get I is equal to j. Okay, this shows that I minus j is the multiple of, or mod I minus j is the multiple of m, and the only possibility is I and j are less than m. Then mod I minus j is less than m, and a non-negative quantity. Then the only possibility is mod I minus j is equal to 0, and consequently I equal to j. Okay, this we have already proved in the previous theorems. Uh, for the now we have any two of these residue classes uh, cannot intersect. Now we have to prove that their union is the set of all integers. For that, if we choose an integer x belongs to z, then using the division algorithm, being m is positive, you can write this x equal to m times q plus r. 0 less than r, 0 less than or equal to r less than m. Okay, so this shows that x is congruent to r mod m, implies x belongs to r cap, where we know that r belongs to 0, 1, 2, 3, etc. m minus 1. Now from these two proofs, you can say that 0 cap, 1 cap, etc. m minus 1 cap are disjoint, and then union of all these equivalent classes is z. Now if you replace 0 cap, equivalent class of 0 the same as m cap, you will get the C part, because 0 cap and m cap are same, because 0 and m uh, belong to the same equivalent class or residue class. So using the first part, you can get these two equivalent classes are same. Now we have a definition for complete residue system. A set of m representatives, one from each of the residue classes, 1 cap, 2 cap, etc. m cap, or you can replace this by 0 cap, 1 cap, etc. m minus 1 cap. Both are same. These two uh, residue classes are the same, because if you replace this m cap by 0 cap, then the complete residue system can be defined as a set of m representatives, one from each of these residue classes, either from these, otherwise from this, is called a complete residue modulo m. So we have some examples. If we take m is equal to 3, 0 cap, 1 cap, 2 cap are the disjoint residue systems, then the set 0, 1, 2 is a complete residue system. Or you can choose any representative from this and another representative from this one and a representative from 2, you will get a complete residue system. So every complete residue system corresponding to m is equal to 3 contains exactly 3 elements which are all incongruent modulo m. Now we have a theorem 5.11. Assume k comma m is equal to 1 if set a1, a2, etc. am is a complete residue system modulo m, so is ka, ka1, ka2, etc. kam. Okay, so this is because kai congruent to kaj mod m, you can cancel this k, because gcd of k comma m is equal to 1, so you will get a is congruent to ai is congruent to aj mod m, because ka1 kai congruent to kaj mod m means m divides, this is if and only if m divides k times ai minus aj. This implies m divides ai minus aj because GCD of m comma k is 1. So this m should divide this ai minus aj. Consequently, we have ai is congruent to uh, aj mod m. So we have uh, these are incongruent modulo because whenever these AIs are distinct, we can get KI, K1, K2, etc. KAM are incongruent modulo M. Since there are M elements in the set, it forms a complete residue system because these are all incongruent modulo M and it contains exactly M elements. Okay, so this form a complete residue system. Okay,